Look at the sheer density of engineering in a modern particle detector. Millions of sensors and miles of wiring, all working in perfect synchronization to track the smallest building blocks of reality. Or consider a deep space observatory. We can pinpoint the chemical makeup of galaxies billions of light years away. This is humanity's mastery of objective data over superstition. The standard historical narrative tells a very specific story about how we got here. It suggests that rigorous physical inquiry died out with the ancient Greeks, only to reappear during the 17th century Renaissance with figures like Galileo and Newton. Between those two eras sits a 1,000-year stretch commonly dismissed as the Dark Ages, a period supposedly devoid of reason, logic, or intellectual progress. But complex systems do not materialize out of thin air. Modern science requires a highly specific instruction manual, a methodology of testing and proving that the ancient Greeks simply did not possess. In the medieval world, you had two distinct groups. Artisans possessed practical, hands-on skills for building cathedrals and forging steel. Meanwhile, scholars debated abstract logic in monasteries. They were completely separate disciplines. So how did the thinkers of the 17th century suddenly know how to bridge that gap? How did they learn to take abstract mathematics and apply it to physical, real-world testing? To find the true origin of the experimental method, we have to bypass Newton and rewind exactly 4 centuries to a largely forgotten medieval scholar in England. In the early 1200s, Robert Grosseteste was a central figure in the intellectual growth of the newly formed Oxford University. He served as its first chancellor and became the primary organizer of its philosophical studies. By 1235, he was appointed Bishop of Lincoln, commanding one of the largest and most powerful dioceses in England. His career exemplifies a specific medieval tradition where the rigorous study of nature was considered an essential component of theological understanding. Grosseteste held a specific obsession, the physics of light and optics. He believed light was the first form of matter created in the universe. But when he tried to accurately explain phenomena like the rainbow, he hit a wall. He recognized that the physical universe operates on strict economical mathematical principles, rather than random divine whim or magic. Ancient Greek logic could construct a beautiful argument, but it couldn't prove why a rainbow appeared at a specific angle. Grosseteste realized that a completely new, structured analytical framework was required to truly comprehend physical reality. He developed the method of resolution and composition. First is resolutio. You observe a complex effect, like light refracting, and strip away variables to isolate its fundamental principles. Then, compositio. You use mathematics to rebuild the phenomenon from the ground up, predicting how it behaves. This double path finally bridged the historical divide. For the first time, abstract theoretical math and practical, observable reality were tied together in a single, repeatable loop. Still, a major problem lingered. In ancient philosophy, a theory only needed to be logically sound in a debate. It could be argued perfectly in a monastery, yet fail completely when tested against the harsh reality of the physical world. Grosseteste solved this by introducing the strict requirement of experimental verification. A theory had to be tested against physical reality. This led to his concept of falsification. If an experiment fails to produce the predicted results in the real world, the theory must be discarded permanently. It does not matter how elegant or mathematically beautiful the idea is. He anchored this testing process in the principle of parsimony, the understanding that nature is inherently economical and always operates in the simplest way possible. By establishing that physical nature, not human debate, is the ultimate arbiter of truth, Grosseteste forged the core engine of the modern experimental scientific method. This methodology did not die with him. His most famous student, the Franciscan friar Roger Bacon, meticulously recorded and expanded Grosseteste's exact procedures, transmitting them across the universities of Europe. Together, they established what became known as the Oxford School, an academic tradition that permanently cemented the marriage of mathematics and experimental physics. Modern historians of science have tracked this exact lineage. This text from Dr. A.C. Crombie details how Grosseteste successfully united the experimental habit of practical artisans with the rational explanation of philosophers. As the document notes, he founded a school of science at Oxford which carried on his work. specifically his ideas on induction, experiment, and the use of mathematics and physics. These methods were codified in scholarly texts and transmitted through academic circles for generations, providing the methodological foundation that would later be utilized by the scientific giants of the 17th century. When figures like Francis Bacon, Galileo, and Isaac Newton conducted their famous experiments, they were utilizing an intellectual framework whose core components had been assembled centuries earlier by Robert Grosseteste. The supposedly Dark Ages were actually the era when scholars began assembling the core principles of evidence and mathematics that continue to drive our discoveries today. If you want to continue discovering the forgotten minds that built our world and unravel the gears behind history and science, subscribe to the channel now and activate the notification bell. Leave your comment. What other scientist forgotten by history should we investigate? Until the next The Explainer.